Swayam Prabha, free DTH channel for education.
Okay, so what we will do in this class is we would first relook at what we have already seen in the previous class. Some of the salient points we will relook at it. And in addition to that, we'll also go in more detail into some aspects of what we have already discussed. And followed by that, we will be also looking at, we mainly focused in the previous class at the microscopic level phenomena. Of course, we had a whole general idea has been given there, but more focus we have put on the microscopic level phenomena. So in this class, we would also look at things at macroscopic level. So that's the idea for this class. I'll share my notes and I'll go in that flow of points. Right, not this one. Okay, yeah, this is the new notes I prepared for this class. Okay, so what we are talking about is nuclear magnetic resonance, okay, which is referred to as NMR. One misinterpretation with not so technical people is this nuclear has something to do with whatever is there in nuclear medicine. Okay, there is a radioactivity when it comes to the nuclear medicine. What are the modalities that we have discussed that falls under nuclear medicine? Did we discuss any modalities that fall under nuclear medicine?
PET scan.
Right, PET scan and any other? In fact, X-rays and CT also could fall under nuclear medicine. Okay, where there is a nuclear radiation. So there is a radioactivity phenomena going on. As you could see in the electromagnetic spectrum, that's on the other end of it. So first to be clear, in the nuclear magnetic resonance imaging, whatever we are saying in nuclear is concerned with the nuclei of atoms. That's what the focus of it. That's the first point. Then we started in the previous class discussing about the properties of atoms that have odd number of protons in its nucleus. So there is at least one single fellow there who is free to do whatever he wants to. He's not coupled it to any of the other proton. So it has in any way the protons have a charge is there, a mass is there. Another fundamental property of this proton is it spins, right? And the angular momentum of this spin is a well-known concept in quantum physics, where you give that, let's call that angular momentum by s bar, then it will be equal to h hash into I bar, where h hash is nothing but h by 2 pi, h being the Planck's constant. Notice this angular momentum is in, you could think of it as in a three-dimensional space, which you could represent as a vector of, let's say, angular momentum in x, y, and z respectively. Similarly, this quantum number is also a vector, okay, I bar. And if you consider a hydrogen atom, for instance, for example, and also other atoms that we have discussed, carbon, fluorine, sodium, and phosphorus, all of them have uh, a value of plus or minus 1 by 2 in the z direction. Okay, that again, it has similar values in x and y as well. So that's basically your spin quantum number. So just an illustration here, you have an atom that is now, it's a charged a charged proton or charged nucleus. This is spinning. Okay, when this is spinning charged atom, what would happen then? What is the result of it? When a charged particle, a rotating a particle which is charged is rotating, so what would that generate now? From your Maxwell's equations, what is it going to generate?
Magnetic field.
Right, a magnetic field. So it acts like a small tiny magnet, having, depending on its rotation, it has its north pole and south pole, and it keeps rotating. If you take either a sample, or if you take a voxel volume of an size or something like that, there are millions and millions of atoms in it. Okay, all these are now, they will rotate in their own direction. So for each one it has its own north and south. Okay, all of them overall, we know from the probability theory, there is no control here, there is only chaos. So the net magnetic field is zero. In other words, what I could say here is, at microscopic level, at atomic level, there is magnetism. But when you see at macroscopic level, its magnetic field is essentially zero. That's what it is going to happen here. And suppose, let me first, then what we did is, what is the magnetic field strength of this proton? That's what we computed here. How do you know that? If you know at what rate it is rotating, then the magnetic dipole moment for that single proton, in this case, if you consider the hydrogen, is gamma times s bar, where this gamma gives you the gyromagnetic ratio. That's the that is again the property of a given atom. That's the gyromagnetic ratio times this angular momentum. Basically, the faster it rotates, higher the magnetic field generated. And in addition to that angular momentum, this value of magnetic dipole moment that got generated also depends on the nature of the atom. So that property of atom is in a way embedded in this gamma, right? So then you write it in terms of angular momentum, this one. To give you an idea, I am just putting the same table in a different perspective, which should be telling you what is the gyromagnetic ratio for different atoms. There earlier I kept this table while talking about the Larmor frequencies. Their Larmor frequency being gamma by 2 pi into B naught, the applied magnetic field. Okay, we have taken certain value of B naught equal to 1 and we kept these values. Suppose you forget about B naught, then it is equivalent to gamma by 2 pi. And you could also work out what would be the units of it. It turns out to be megahertz per Tesla, heads per Tesla, but we wrote it that. So anyway, you ignore this normalization factor for a moment, but just look at the kind of values for different atoms. These are essentially the atoms which we find in our body, right? And we are interested in those things. Say, for example, this would be for hydrogen, this gamma would be around 42.5, 42.6 megahertz per Tesla. And then carbon 10. So out of them, you could see among all hydrogen, carbon, fluorine, sodium, and phosphorus, you have hydrogen has a very high value of gyromagnetic ratio. Okay. Another point we already discussed is, in our body, water is there almost 70%. Water has hydrogen, H2O basically. So in that molecules of water, you have hydrogen atoms. So that is in abundance in our body. And that's what we are using as our source for getting that is something which we are behaving like a magnet and getting responses from them under a controlled environment. And that's how we are getting the imaging of a given object. And just to add that, it's not just the water, it's the fat that is there in our body also has this hydrogen atoms. That's the additional point I wanted to add here. Okay, now after that, what we discussed, as we were just shortly seeing, all of these atoms have these are spinning in their own orientations. So now if you want to see the whole magnetic moment, if you add this being a vector quantity, this mu bar magnetic moment is a vector quantity. If you keep add everything either in a given sample, in case of where you are studying the chemical decomposition of or chemical composition of a given molecule or a sample, chemical sample, or in a voxel space, whatever you have there, within that, all of them would eventually, the sum would be 0. Now, how to get some macroscopic level magnetism out of it? So the idea is you apply a very strong magnetic field, and that magnetic field would polarize these atoms of hydrogen atoms, and are, in other words, these magnetic dipoles, and would give you the magnetic field. Okay, and this property of spin system is nuclear. So whatever you are getting now by applying a external magnetic field is also referred to as nuclear magnetism. Okay, now if we considering now a special case where, assume that your sample is in the xy plane, you are applying to that a magnet, yeah, in whatever it is. Now you assume that you are applying a magnet. Okay, ignore that statement. Assume that you are applying your magnetic field in the z direction. Okay, our intuition tells that there is a force here, everything should go into that direction. Okay, but quantum physics predicts it otherwise, and which is in fact true, is that it's not just one state. This could spin in only two quantum states. It cannot spin randomly, or it cannot spin just in the direction of b naught, but it spins in parallel and in somewhat and in anti-parallel states to the applied field. Okay, one thing I have not made explicitly clear in the previous class, just to keep it general, is that this in fact doesn't just come in this direction. If my z is this way, this atom doesn't just come in this way, but it rotates around its axis. This is what. So hopefully this, you just look at the upper cone here, so it keeps rotating. If you take hydrogen, it rotates at an angle of 54 degrees. How this 54, will not go into that quantum details there, but this, it has two spins. Okay, either once you apply this magnetic field, it either rotates at 54 degrees here, or in the opposite direction 54 degrees. So in other words, it either rotates at 54 degrees, or if you are measuring angles with respect to this positive z axis, or at 180 minus 54. Okay, at 126 degrees, that's where it rotates. That's how it rotates when you are applying an external. This is the first time we are applying an external magnetic field. There are only tiny magnets which are there in their own orientations. Now it's time we applied an external magnetic field. So then it is rotating at an angle of either 54 degrees or 126 degrees. That's what it is happening now. Here there is a slide. When you apply an external magnetic field, what quantum physics tells us is there is slightly more preference for atoms to rotate in 54 degrees, that is being in a parallel state to the applied field. So there is a slightly more preference. This, how much would it be? We have discussed in the previous class, where we worked out that suppose if you have a field of 1.5 Tesla magnetic field that you are applying, okay, and assume that you are looking at 2 millions. Out of 2 millions, okay, 1 million plus 7 would be in the parallel state, and 1 million minus 7 would be in the anti-parallel state. So 1 million plus 7 would be rotating in 52 degrees, and the other would be 52 or 54 degrees, and the rest 1 million minus 7, when you are applying a 1.5 Tesla field, would be rotating in the anti-parallel state. So now, however, you could see now there is indeed at least a weak magnetic field, and added to that, you have millions and millions of hydrogen atoms in abundance for, even if you take an space. So that is good enough in a way to generate the some magnetic field. Okay, that's what you could observe now. Overall, a magnetic field is something you could observe here. Okay, and then in terms of quantum physics, if you look at it, so you could see now we are making slight gradually a transition from an atomic level, from a microscopic level to a macroscopic level. In other words, from an atomic level to an oxel level or a sample unit sample level. So this is what it would rotate. And then if you took put together effect of all together, then there is also a macroscopic magnetism. How do you get that now? So this is a bulk magnetization vector m bar. As we discussed, there is a little slightly more bias towards the parallel state, which is also a low energy state. That working we have done in the previous class. And how do you get that m bar? That is equal to, you have, let's say, total number of atoms, hydrogen atoms you have in a given sample, or you could consider it as in a oxel space that you are currently looking at. Okay. Or you have tuned to is ns, total number of samples hydrogens you have, you sum all of them together. Okay. So then what it tells you, what can you know about what would happen this magnetic field is, if the sample is left undisturbed in the static field b naught for a long period of time. Okay. Right now, long period, you just keep that word in your mind. What exactly this is, what is a long period, what is a short period, how is it going to vary, that we will see in the upcoming classes. Then m bar will reach an equilibrium value of m naught that is parallel with the direction of b naught. So what we are talking about here is everything is in a random state now. You applied b naught. When you apply b naught, it's not like in t equal to 0 plus instance itself everything would come into either parallel and anti-parallel state. It takes a while. This is also a very important information that is explicitly exploited while applying this magnetic fields and even perturbations to this magnetic field. So just keep in mind about this for a long period. So once you apply it, you wait for a sufficiently enough time, and that is when you see an m bar here, okay, which we are referring to after a sufficiently long time. Whatever you are getting is a stabilized version you will get, maybe thermal equilibrium you may call it. Okay, that time whatever magnetic field is there, we are only right now talking about that value m naught. Okay, again we will not go into the derivation of this because it would require us going through a lot of physics. Okay, so that's we would like to deliberately avoid. We will just see what does the interpretation of this equation, that's what we would focus here. So look at here now, what we are, the statement we are making is, you have a sample, you are applying a magnetic field in one direction, that's in the z direction. Okay, you kept the sample, you applied a magnetic field there. Then whichever earlier the overall magnetic field, if you call it as m bar, is 0. Now if you wait for sufficiently enough time, this m bar will be in the direction of b naught. Okay, applied magnetic field b naught. And the stabilized version or the steady state version, okay, if you look at in terms of the transient currents and steady state currents or voltages, in the similar terminology you use here, the steady state magnetic field that you observe for an applied b naught, okay, is given by this one, where 1 by 4 times k into t multiplied with b naught gamma square h slash square and pd. So here k is the Boltzmann constant. Okay, it's a constant, so no worry about that. T, capital T, is a temperature from absolute zero. So from zero absolute, I think that means Kelvin, I guess. You need to refer that. I don't exactly remember. So that's temperature. Okay, probably if you are bringing your sample to a lower temperature, that would increase your m naught value. Anyways, at least while sampling, while trying to acquire the images of humans, you don't try to control the temperatures of humans to bring them to lower temperatures. Okay, so that's also you could, for the time being, in case of humans, while you are scanning, you consider that a constant one. Then you could observe here, this m naught that you are going to get, the magnetic field that you are going to get out of that sample, is proportional to the applied magnetic field, whichever you have external magnetic field b naught you have applied. So the more the applied magnetic field, you will get this m value larger, and vice versa. Similarly, this gamma is what? Gyromagnetic ratio. That's a constant for a given atom hydrogen. We already know gamma by 2 pi 42.6 megahertz, right? That's constant, nothing to worry about that. H, H slash is nothing but H over 2 pi, right? That's equal to the Planck's constant. Again, constant, don't worry about that. And the next term you have is proton density. What does, we are calling this as proton density? Anyway, when you consider an hydrogen atom, you are talking about there about a single proton there. So that's why this is also referred to as proton density. This is number of targeted nuclei per unit volume. What it is going to tell you, suppose in that unit volume you are considering, if it is a very tightly packed one with lot of atoms within, a lot of nuclei within that unit volume, your m naught, the signal magnetization you are getting out of that signal would increase, and vice versa. So this is again something that is explicitly exploited while you are getting the images of, be it humans or any animals or any living beings, where, for example, if you consider the scan of MR scan of your head you are trying to do, we'll come back in the next classes how you would focus getting the signal from just a particular voxel, that we will see later. For the time being, assume that you would be able to manipulate your system in a way that you could get response from just a single location. Okay, and compare that location with another location. Suppose in that particular location, whichever structures you have, the proton density of these structures could be different from the structures that are there at a different location. Then you could distinguish both by looking at the resulting m naught values that you are going to get in the z direction. And this is what could give you the contrast in the image when you are moving from one structure to the other structure. Okay, this is one aspect of the characterization of the structures. There are other things, like for example how fast it would recover, how fast when a perturbation is given it will go to that. Those all things we will discuss it in next class, which were T1 T2 relaxation times T1 and T2. But this is another clear distinct difference that you observe while looking at regions that have different tissues, which can be characterized or differentiated with the help of having different proton densities. Then they would be resulting in different m naught values. Okay, is that point clear? Right, that's what I'm saying here. So you could see both the larger values of b naught and larger values of pd proton densities, you get higher signal of m naught. And of course when you are imaging it, you are keeping your b naught applied magnetic field is constant for both the tissues. So this is getting affected only by this term pd here, proton density. Okay, so uh, these spatial differences in PD will give rise to signal differences, which in part accounts for image contrast. Other issues are also there, which we would discuss shortly. In the next class, that part we will be discussing. Then, um, as I mentioned here, we are talking about after a long period, sufficiently long period of time, your m naught, which is initially 0, when you are applying b naught, will come to in the direction of b naught, resulting in a value of, let's say, m naught. But thus that should already tell you that this is something dependent on time. It's like in your circuits analysis, you should say your voltage and currents in a circuit where you are having an AC source and have elements like inductor and capacitor. You should be, it's very clear that the currents and voltages are dependent on time. In similar way, your, the magnetization that you are getting, this magnetization, bulk magnetization vectors are also dependent on time. And of course, they are also spatially m bar. The moment we are saying already this m bar here, okay, this since given that you have applied in the B naught that you got it here, but make a note here, this is not only B naught that we apply, there is another magnetic field also that we are going to apply, right? Let's say that is what we were saying gradient magnetic fields are there, right? That's also something you are going to apply, which would have, you would see in addition to B naught, there will be another B plus B, which varies with time, X, Y, Z, and T, as time as well as spatial location. That's what you are going to see in the upcoming classes. So what you could say here is m bar is equal to m of, it's in fact a function of not only spatial locations but also time. That's why you say it as m of X, Y, Z, and T. Okay, then that's what we more or less, other than adding few points, particularly this m naught in equation and the interpretation for it, the rest more or less we discussed in the previous class, with of course with other things which we have not gone through them in the current class. Okay, now what we are going to see now is, we have seen earlier the spin angular momentum, right? The spin, it is rotating at an angle, okay, and that spinning of this charge is giving you a dipole effect. Similarly, there is now spin angular momentum is at a microscopic level. Now you could observe now an angular momentum at the macroscopic level as well for this m bar. See, just to draw parallels there. Mu is something magnetic dipole moment at the micro scale, and that is related, mu is related to the angular momentum s bar. Similarly, at a macroscopic level, the magnetism that you have now is m bar, and that at a macroscopic level also would give you the angular momentum. Okay, that is associated with this m bar. And now this at a macroscopic level, you can come back to the classical mechanics here, which would tell you that so you have written there, for example, microscale, how are they both related? The magnetic dipole moment is gamma times the spin angular moment. Now at a macro scale, if you come, this magnetic dipole moment is now whatever you are observing, this magnetization vector m bar. Okay, when I am saying m bar, make a note that it's not just function of xyz but also function of time as well. So this is a function of xyz t is gamma times now the angular momentum, the mechanical classical mechanics, whatever angular momentum you have been studying there, that we are referring to it as j bar here. Okay, so m bar is gamma times z bar. Okay, and now if you have a rotating vector m bar is there, okay, which is there, and then you could, when you are applying a force to it, okay, that could, which could be, for example, the applied magnetic field here is working on it, and that would result in torque. So again, I'm sure you are all familiar even from your +2 physics that this is rate of change of angular momentum is equivalent to the torque, right? And rate of change of angular momentum is this, j is your angular momentum at the macroscopic level. So this I am writing it as dz bar by dt, that is equivalent to, and uh, that is torque, equivalent to torque. How can you give a torque when you are applying, let's say, a force b bar on a vector of m bar? The cross product of them would give you the torque. So dz bar by dt is equal to m bar of t cross product of it with b bar of t. Okay, we want to get rid of this j bar and put everything in terms of m bar. So you multiply both sides with gamma. So gamma times j bar would give you m bar. So dm bar by dt is equal to the right hand side, just a multiplication with gamma. So gamma times m bar of t, cross product of it with b bar of t. Is it clear so far? So after this, actually, what we would be doing it, I think I will just for making it modular, I would rather stop the discussion here. But later, what we would do is, as I was mentioning, I would just give you kind of a glimpse of what we will be doing in the next class in detail. Assume that something is there at a, again, you could make interpretations about the frequencies, resonant frequencies at the macroscopic level also. Larmor frequency you could derive from here also at a macroscopic level, which would result give you a similar result as you are seeing on the other side. Now, just what we would be seeing in the upcoming classes is, in the next class is, how does this m bar could vary when you are giving, in addition to this external applied magnetic field, some other magnetic field, which is, let's say, in the xy plane. So this you are applying in the z direction. In the xy direction perpendicular to it, if you are applying a force there, so that I could call it as some bxy of t. Okay, in the xy plane I am giving some magnetic force applying there. So you could think of it as a top which is rotating. You give a force here, okay, then what would happen? It starts rotating this way. So assume that everything is rotating at z only initially. Now, depending on the force you are giving it, the top would rotate this way, right? And then you withdraw this force, then what would come? It would slowly, from that angle, it would slowly come here, and this m bar would again come into the direction of z bar. Now, this m bar interpretation, how is it varying? You will see in the next lecture that you could interpret this value, how its value is varying on with respect to the z axis, okay, which is referred to as the longitudinal plane, and in the xy plane, okay, that's called as transverse plane. The xy plane is called as a transverse plane, and the z plane is called as a longitudinal plane. You apply in the x direction, okay, you are poking it, okay, it's like a top is rotating, you just put a force there, then it would slowly, its angle would come down, right? But while the top is rotating, there is no constant force here, but there is a constant magnetic force here which is pulling it up to always come in the z direction. Now you are poking it and then leaving it, so then what would happen? It would come like this and then again come back here. So you could already make a guess here that as time progresses, this would be m naught. But meanwhile, from the moment you withdraw your force there, at that point it is least, and then this would come here. In terms of mz, you have a minimum value at that time, and then this would again come back here, and finally it settles down to m naught. Okay, this settled down again. We are looking at a macroscopic level. This lattice structures and everything, if you start looking into it, then you do a similar analysis, and which gives you a different perspective. You could do it at quantum level as well. And now if you look at what happens to the magnetic field in the xy direction, this field is maximum when you just stopped poking it. You poked it to the extent, to the maximum extent, you poked it for some time, you left it. So from there it will, because there is a pulling force in the z direction, this would eventually come to the z direction, and in the xy plane its component would be equal to 0. So those are, and how much time it takes for mxy to become 0, and for mz to regain to its normal value. So these two constants is where the times are different, in fact, okay, because their multiple atoms are spinning, okay, while spinning also they are spinning at a different phase, okay, they might be rotating at the same angle, but the starting points could be different for each of them. It will only bring them into parallel state, but the starting points are different. In other words, that starting point is for us is 5, right? If you have something like a sine omega t plus 5, omega is same for all, but this phi value could be different for all of them. So, and then there is other things in quantum level, lattice structures, and other things which I myself also is not very clear. So based on that, you would see, and hopefully we'll get some intuition on why they are different as well to an extent, that this constants for how this mxy and mz are regaining to its final settle down values would be different. Those are you refer to as t1 time for one constant, and another constant you call it as t2 time. These are similar to in a capacitor e power, you are getting its charge, okay, its voltage equal to 1 minus e to the power of minus t by t. You get a similar equation. You get one t1 for mxy and another t for mz. Okay, those are t1 and t2 times that you would come across in case of the MR imaging. Okay, so those details we will discuss in the next class. So here maybe I'll stop the recording part.